Think about the sheer scale of our Milky Way, this colossal spiral we call home. We often marvel at distant galaxies, but, right at the very center of our own,
Hmm.
a region just brimming with stars, yet hidden by all that dust, lies a key to understanding how our entire galactic structure, well, how it came to be.
That's absolutely right. Well, we have a pretty good handle on the Milky Way's grand design.
Mm.
Its spiral arms, the vast halo of stars surrounding it, the galactic center, the bulge, has always been a tough nut to crack.
Right.
It's like the oldest part of some ancient building, the hardest bit to actually access and study properly.
And that's precisely where we're diving deep today. We're zeroing in on the formation of the Milky Way by looking really closely at its most ancient stars.
Yeah.
Those ones with the fewest heavy elements, the metal poor ones, living right in that central hub.
And our primary source for this whole exploration is a really compelling piece of recent research,
Mhm.
The Poor Old Heart of the Milky Way by Ricks and colleagues from 2022. This study uses the incredible power of data from the Gaia Data Release 3. It gives us this unprecedented glimpse into a really pivotal era of our galaxy's history.
So our goal today is to really pull out the most significant findings from this paper. We want to understand the Milky Way's origin story, focusing on the evidence that's locked within these ancient stars right at the center.
Hmm.
And it's worth remembering, isn't it, that looking into this region is a real challenge. You're battling like immense distances and this thick veil of interstellar dust.
Absolutely. I mean, compared to the halo or the more accessible disk, the inner galaxy presents these huge obstacles. The sheer distance makes precise measurements incredibly difficult.
Yeah.
And the interstellar medium, just packed with dust and gas, it blocks so much of the light. Astronomers call this extinction, and it's a major problem there.
It really sounds like trying to excavate an ancient site where just layers and layers of sediment and debris obscure the oldest artifacts down below.
That's a good analogy.
We've made significant progress mapping the galactic halo, though, haven't we? Identifying the remnants of smaller galaxies like Sagittarius and that Gaia sausage Enceladus thing.
Indeed, yeah. Those galactic collisions, they left really telltale signs, streams of stars, tidal debris, which we can now map, largely thanks to these extensive sky surveys.
Right.
And the Gaia mission has just been revolutionary. It gives us incredibly precise positions and motions for, well, billions of stars, allowing us to trace these accreted components out in the halo.
Okay, so the halo story is definitely becoming clearer. But what hints did we have about the inner galaxy's ancient building blocks before this recent work by Ricks?
Well, there were some intriguing clues emerging from earlier research, studies using globular clusters.
Oh, yeah.
Those dense collections of very old stars. Using them as tracers suggested the presence of ancient structures deep inside the inner galaxy. People proposed things like Kraken and Koala as potential remnants of really early accretion events.
Kraken and koala, I mean, those names certainly paint a vivid picture of the early, maybe chaotic Milky Way.
They do. They capture that sort of dramatic nature of galactic mergers. And more recently, Belokurov and Kravtsov, using earlier Gaia data, identified a potential in situ proto-galactic structure they called Aurora.
Aurora, okay.
Yeah, its stars showed very little rotation, which kind of hinted at a very early formation time, perhaps even before the Milky Way's disk fully spun up and formed.
Mhm.
And then Conroy and colleagues, they pinpointed individual proto-galactic stars with just extraordinarily old ages, over 13 billion years old,
Wow.
characterized by these very, very low levels of heavier elements.
Wow. So these earlier findings were definitely suggesting there was something ancient lurking in the inner galaxy. But this new research by Ricks et al., it aims to give us a much more detailed picture of how the Milky Way actually formed in those earliest stages, right?
Precisely. And to understand that, we really need to think about the framework of hierarchical galaxy formation, which basically proposes that large galaxies, like our Milky Way, grew over cosmic time through the merging of smaller galaxies.
Right. The little things make big things idea.
Exactly. And this leads to a really fundamental question about the oldest, most metal-poor stars we see. Did they form within the primary building blocks that first came together to create the proto-galaxy, what we'd call in situ formation?
Mm-hmm.
Or do they actually originate in separate, smaller galaxies that only later merged with the main body? Accreted, basically.
That's a key distinction, isn't it? It's like asking if the foundation stones of a building were quarried right there on site or if they were brought in from somewhere else entirely.
Yeah.
And I can imagine it's incredibly tough to differentiate when you're looking back billions and billions of years.
You're absolutely right. especially in the very early universe at high redshifts. When the universe was maybe less than a billion years old, major mergers between galaxies of comparable size could have happened really rapidly. And that just blurs the lines between what was truly in situ and what was technically accreted in those first moments.
Okay, so this brings up a bit of a challenge in terminology then. How do we even define in situ and accreted in those really early chaotic times?
Exactly. And Ricks addressed this head-on by adopting a specific terminology in their paper. They suggest that all the major pieces that came together very, very early, let's say at a redshift of 5 or even greater,
Okay, very early.
should just be collectively termed the proto-galaxy.
Yeah.
This sort of avoids the difficulty of trying to single out one component as the sole in situ progenitor when maybe several big things merged quickly.
Ah, I see. So group the initial main assembly together.
Right. Then, anything that gets added later at lower redshifts, well, that could be classified as either in situ if it was, say, new gas falling in and forming stars within the main galaxy,
Uh-huh.
or accreted if it was a fully formed stellar system like a dwarf galaxy merging in later on.
That makes a lot of sense, focusing on that main initial assembly rather than getting sort of bogged down in labeling every tiny early component. So how did Rix and their team actually use the Gaia DR3 data to probe this proto-galactic heart?
They really, really exploited the unprecedented detail in Gaia DR3. Their study focused specifically on metal-poor giant stars
Giants.
within a relatively small radius of the galactic center, specifically inside 5 kiloparsecs, so quite central.
Right, in the core.
And they used the low-resolution BPRP spectra from Gaia, that's the blue and red photometer spectra, to estimate the metallicity.
The heavy element content.
Exactly. The abundance of elements heavier than hydrogen and helium, which is a key indicator of a star's age and origin. Crucially, though, they combine these metallicity estimates with the radial velocities from Gaia's radial velocity spectrometer, the RVS.
Ah, so you get the full 3D motion?
Precisely. That allowed them to determine the complete three-dimensional orbits for an astounding 1.5 million stars in the inner galaxy.
1.5 million stars. That's just an incredible amount of data to work with.
It really is.
So their main goal was to figure out if there's a significant population of these old metal poor stars right there at the Milky Way's core.
Mm-hmm.
And crucially, whether these stars are part of a sort of tightly bound proto-galactic component or if they're just stars from accreted galaxies passing through the inner regions on their orbits.
That's exactly it. And the sheer scale of their sample, it allowed them to make some truly compelling discoveries.
Like what did they find?
Well, first off, they identified vastly larger numbers of metal-poor stars in the inner galaxy than any previous study had managed.
Okay.
We're talking over 4,000 stars with very low metallicity, MH less than -2,
Wow.
more than 20,000 with metallicity less than -1.5, and a whopping 70,000 with metallicity less than -1.
70,000.
So just the sheer number of these ancient metal-poor stars they confirmed in the center was a real game changer. It really solidified this idea of a massive primordial core to our galaxy.
Wow, those numbers really do underscore the significance. And what about their distribution in orbits? Are they just scattered everywhere in the center?
No, their analysis strongly suggests that these metal-poor stars, especially the really metal-poor ones, like MH less than -1.5,
Mm-hmm.
are very centrally concentrated.
Okay.
The distribution of their parallaxes, which, gives us their distance, indicates that most of them actually reside within that 5 kiloparsec radius of the galactic center.
Right near the middle.
Yeah. And furthermore, when they reconstructed the orbits of these stars, they found that the majority have their apocenters, that's the point in their orbit, furthest away from the galactic center,
Uh-huh.
also within that same 5 kiloparsec radius.
So they're really stuck there. They're not just visitors passing through. They seem to be gravitationally bound deep within the inner galaxy.
That's the strong implication, yes.
But I remember you mentioning earlier that some metal-poor stars could actually be halo stars on these really elongated eccentric orbits just caught near the center. Did Rix et al. Find evidence of that population too?
Yes, they did. While the majority of the metal-poor stars they looked at in the inner galaxy are tightly bound, they definitely identified a smaller, but still significant number of stars,
Okay.
particularly those with metallicity, less than about Menical 1.2, that are on these high eccentricity orbits, the kind that swing way out beyond 10 kiloparsecs.
Ah, the interlopers.
Pretty much. These are likely members of the accreted stellar halo, perhaps remnants of that Gaia Sausage Enceladus merger event, that are just currently near their pericenter, the closest point in their orbit to the galactic center.
Okay, so we've got these two distinct groups, it seems, of metal-poor stars hanging out in the inner galaxy, this centrally concentrated, tightly bound bunch, and then a more dispersed group on these wider, more eccentric orbits.
Hmm.
So how did they actually figure out if these groups had different origins, proto-galactic versus accreted?
Well, this is where the detailed chemical compositions become absolutely crucial.
The chemical fingerprinting.
Exactly. Ricks and the team used data from the Sloan Digital Sky Survey, SDSS, specifically the APOG survey within it, to examine the abundances of specific elements.
Okay.
Things like the alpha elements, magnesium, silicon, calcium, those ones.
Right, formed in massive stars.
Yes, and also elements like aluminum and manganese, all relative to the amount of iron. And what they found was really telling.
What was it?
The stars that are tightly bound, the ones staying within the solar radius, they have abundance patterns,
Mm-hmm.
particularly high alpha element ratios that are really consistent with a proto-galactic or, in situ origin, formed quickly, deep in a potential well.
Okay, makes sense.
Conversely, the stars on those high eccentricity, wide-ranging orbits, they displayed abundance patterns typical of accreted stars.
Ah.
Their chemistry looked much more like what we see in the remnants of disrupted dwarf galaxies,
Hmm.
very likely Gaia Sausage Enceladus.
That's a really powerful way to distinguish them, isn't it? Different formation environments literally leave these distinct chemical fingerprints on the stars.
Exactly right. And they uncovered another really intriguing piece of the puzzle by looking at the rotation of these different stellar populations.
How fast they're spinning around the
Yeah,
galaxy.
the net galactic rotation. They calculated this for stars grouped by their metallicity. And what they found was a clear trend. The most metal-poor stars, those really ancient ones with MH less than Merida 2,
Uh-huh.
exhibited very little, essentially, no, net rotation. They're moving around, but not in a coherent, spinning disk-like way.
Kind of random orbits.
More pressure supported, yeah. But then, as the metallicity of the population increased, so looking at slightly less ancient stars, maybe MH around metal 1.5 or metal 1, so did its average rotation speed.
Ah. So the slightly younger, slightly more metal-rich stars in the center are rotating faster.
On average, yes.
That sounds like a picture of a galaxy gradually settling down and spinning up as it evolves over time.
That is precisely the implication. It suggests the very early proto-galaxy was probably a more turbulent, less rotationally supported system,
Uh-huh.
more chaotic. Then, over time, gas falling into the galaxy likely settled down into a rotating disk structure,
Hmm.
and subsequent generations of stars formed out of this rotating gas.
Which was getting more enriched.
Exactly. Getting more enriched with metals over time, leading to this correlation we observe today between higher metallicity and higher net rotation.
Okay, so putting all these pieces together, the sheer number of stars, their tight orbits, their unique chemistry, this rotation trend, what are the really key implications? What does this tell us definitively about this proto-galactic heart of the Milky Way?
Well, these findings, taken together, provide really strong support for the idea that the Milky Way possesses this very ancient, very central component, this proto-galactic heart.
Hmm.
It seems to have formed from the very earliest mergers, the initial coalescence of the galaxy's main building blocks.
Yeah.
The fact that this low metallicity population is so tightly confined, mostly within 5 kiloparsecs,
Yeah.
that really argues against it primarily forming from the slow accretion of distant satellite galaxies over billions of years.
Yeah.
These stars seem to belong right there.
They formed near the center, or their progenitors did.
Right. And furthermore, that high abundance of alpha elements we talked about, seen in the vast majority of stars with MH less than minus 1.5,
Uh-huh.
that suggests really rapid chemical enrichment happened within a deep gravitational potential well.
Yeah.
That's much more likely to have occurred right at the center of a massive early halo where star formation could be intense and rapid, rather than within a smaller, less massive satellite galaxy which would enrich more slowly.
That makes sense. You need that deep gravity well to hold on to the supernova products and enrich quickly.
Precisely.
And they even managed to estimate the mass tied up in this ancient heart, didn't they?
Yes, they did. Based on the stars they could clearly identify, they estimate the stellar mass of this metal-poor component within 5 kiloparsecs to be around 50 million times the mass of our sun.
50 million. Okay.
But, and this is important, they also point out that there is significant dust obscuration in the inner galaxy.
Ah, the extinction problem again.
Exactly. Which means the total mass, including all the stars hidden from view by that dust, is likely considerably higher, perhaps exceeding 100 million solar masses, maybe more.
Wow, so that's a really substantial amount of ancient stars packed right into the Milky Way's core.
It really is a
Yeah.
significant relic.
And you mentioned earlier the connection to simulations of disk formation. How does this picture fit with those models?
It fits very nicely, actually. That correlation we discussed between increasing rotation and increasing metallicity aligns really well with cosmological simulations.
Okay.
Those simulations depict disk galaxies forming as gas gradually cools and settles into a rotating disk structure over cosmic time. Subsequent generations of stars then form from this increasingly chemically enriched rotating gas.
So the oldest non-rotating stars formed first, then the gas settled, spun up, got enriched, and formed rotating stars.
That seems to be the picture, yeah. The
Yeah.
Rix-Zolfing findings provide strong observational evidence for that sequence happening right in the heart of our own galaxy.
And the actual metallicity of this central component itself is quite revealing too, isn't it? Comparing it to other old parts of the galaxy.
Absolutely. The fact that this proto-galactic heart component has significantly lower metallicities,
Mm.
reaching below MH of -2, even 2.5,
Right.
than even the oldest known parts of the thick disk. Those thick disk stars typically bottom out around MH of Mokaf 1, maybe a bit lower, and have ages around 12.5 billion years.
So this central component is even more metal poor than the old thick disk.
Substantially more metal poor, on average. This strongly suggests that the proto-galactic component predates the formation of the main thick disk, both chemically and almost certainly in terms of its formation time.
Which pushes its formation back really early.
Exactly. It implies it must have formed very early in the universe, likely at a redshift greater than 5.
Wow, that's what, within the first billion years or so of the universe?
Yeah, around that time.
Yeah.
It makes its stellar population almost exclusively ancient, truly relics from the dawn of our galaxy.
It's just remarkable to think that right there at the very center of our galaxy, we have this ancient structure preserved from its earliest, most dynamic formation stages.
Hmm.
It really highlights the incredible power of the Gaia data, doesn't it? To peel back these cosmic layers that were hidden for so long.
Indeed. And Rick Sad themselves make that point very clearly. They note in their paper something like, their analysis reflects the astounding information content of the Gaia DR3 data, particularly the BPRP spectra.
Yeah.
It really is a testament to the incredible advancements in astronomical observation and data analysis that we can now probe these deepest secrets of our own galactic home in such detail.
So, okay, to sort of bring this deep dive towards a close then, the big takeaway is that this Gaia DR3 data has given us this unprecedented look right into the Milky Way's central regions.
Hmm.
And it's revealed this massive, ancient, metal-poor, proto-galactic component. This thing likely formed from the very earliest mergers of our galaxy's building blocks, basically setting the stage for the magnificent spiral galaxy we inhabit today.
That's a great summary. We've seen how the immense challenges of studying the galactic center, the dust and distance, have been significantly overcome, at least in part, by the precision of Gaia.
Right.
And it's offered compelling evidence for these distinct early stellar populations existing right there. The orbits and, crucially, the chemical abundances of these ancient stars are acting like fossil records, aren't they?
Yeah.
Providing these vital insights into the Milky Way's birth and its really early evolution.
It's truly mind-boggling when you stop and think about it, that at the seemingly stable, quiet heart of our galaxy today lies this echo, this remnant of incredibly violent mergers and rapid, intense star formation from billions and billions of years ago.
It really puts things in perspective.
It absolutely does. And it makes you wonder, well, what other secrets might still be concealed within that galactic core, just waiting for future observations, maybe the next generation of telescopes, to uncover them.
That's the exciting part.
What other chapters of our own cosmic origin story are still hidden down there, yet to be revealed? Something to ponder, I think.